Hello everyone, this is Sinjeri, here the second.
And I'm Sayanjang. Here's the third.
Yeah. And thank you everyone for joining us today. And first of all, we'd like to express our sincere gratitude to the Stanford Spaces Graduate Lab and Hilti for hosting this NSS challenge. And we are a student team from Urban Robotics Lab at KAIST, and we are very honored to be mentored by our advisor, Professor Myung. There. And so here's our team members. Lebon, the first one, is our team, but unfortunately he didn't participate this conference. And we commonly have interest in 3D LiDAR SLAM things. And so these are the things that our lab is focusing on, and we handle a lot of mobile robots or quadruped robots or drones like this. And we are studying on very several fields, including control or SLAM or planning things. And so in this competition, we achieved a global RMSE about 0.28 and F1 score with 97.49. And let us briefly explain how we achieved those results. So we will cover the details of the 2025 NSS challenge and our registration pipeline with cubic feet and quattro. And then we will see the refinement using chameleon, and then we will conclude with some final thoughts. So compared to the 2024, there are two key changes in this year's NSS challenge. And the first, the pairwise edge information is no longer provided. So this means we don't know in advance which scans should be matched. So we must find candidate pairs completely from scratch and relying on solely on geometry and learned features. And second, the data set now includes up to 10% outlier scans that do not correspond to any valid location. To handle this, we estimate the overlap ratio between scans and classify low overlap scans as outliers. So our framework consists of two main stages like this. The first stage is multi-way registration. For this, we use cubic feet for local feature extraction and quattro for robust solver. And once the initial alignment is complete, we move on to the second stage, refinement stage using chameleon, which is a change detection model. So we detect and remove regions that have changed due to occlusion or dynamic objects or structural modifications. And then finally, we realign the scans using GICP on static points. So in the first stage, we perform multi-way registration. And we start by selecting a single scan as an anchor node. And this serves as the initial reference frame. Then our other scans are registered relative to this anchor during the first iteration. And once some scans are successfully aligned like this, it becomes part of the growing reference set. And then in each subsequent iterations, neurally matched scans in the previous step become the new target point clouds. So then we continue matching the remaining unmatched scans against these updated targets. So this process continues iteratively and allowing us to perform robust multi-way registration even without any prior connectivity or edge information. So as more scans are successfully aligned, the registration becomes increasingly stable and informative. And to extract local features for registration, we use cubic feet or 3D local feature descriptor designed for global registration. And now this work is just under the submission. And cubic feet is based on the 3D convolutional neural network implemented with torch sparse which is a library for 3D convolution. The network takes both source and target point clouds here and processes them through 3D CNN. And then our graph-based attention model connects the two streams and allowing the network to learn feature descriptors more effectively. Then finally, it performs multi-resolution voxelization as this figure and computes the weighted average descriptor to form some compact and robust local features. So we call this as cubic fit. And this design allows very fast and accurate global registration, even in partially overlapping scans. So cubic fit is also designed to improve both feature quality and matching speed. So during the training, we enhance feature descriptiveness by increasing the proportion of the geometrically detailed points in the loss computation. This allows the network to focus on more structurally meaningful regions rather than flat or ambiguous areas. And during the matching, we further improve speed and accuracy by selecting only a concise set of highly discriminative points. So as shown in the figure, we can see that ground truth correspondences between the original and ours across different data sets. And you can see that our version clearly focuses on some discriminative features more. So, and from now on, Seoyan will take over and continue the presentation.
Then I will start by Quattro part. For global pulse estimation, we use Quattro, a robust registration solver. It is designed to avoid degeneracy even with few correspondences. First, Quattro filters correspondences extracted from cubic fit through a grid-based outlier pruning step. Then it performs quasi-SO3 rotation estimation under the assumption that most relative rotations are dominated by yaw direction in structured environments. Finally, once the rotation is estimated, a component-wise translation estimation step follows to compute the full registration transformation. These decoupled estimation approaches allows for robust registration, even under extreme conditions like low overlap or high outlier ratio. This figure demonstrates one of the key strengths of Quattro. Even with a very small number of outlier correspondences, Quattro is still able to estimate accurate transformations and successfully align the scans. After estimating the initial transformation within the same stage using multi-registration, we further refine the final transformation across different stages through change detection. As shown in the right figure, even at the same location, changes can occur across different stages. These both positive and negative changes can lead to incorrect correspondences, significantly degrading the registration accuracy. Even if we get a consistent map within the single stage, scans from different stages may not align properly due to such changes. Therefore, detecting and removing changed areas is crucial to focus only on stable and consistent geometry. To handle this, we use Chameleon, a dual-head network designed for map-to-scan change detection. This model not only predicts changes between the scan and the map, but also estimate the visibility confidence to robustly detect changes even with occlusion. Furthermore, it is designed to be sensor agnostic, demonstrating strong performance across various 3D sensors and environments. As shown in the right figure, the model effectively detects changes on the NSS 2025 datasets. And our final refinement process is performed in this progress. First, we use initial pulse from multi-way registration to align the scan with the current graph map. Next, we run the change detection between the aligned scan and the map to identify regions that have changed, such as occlusion or structural changes. Once these changes are detected, we remove the dynamic areas from the scan and map. Finally, we apply GICP to refine the alignment, but only using the unchanged, reliable regions. Then we can get more accurate results via change detection. So now on, we tackle the NSS 2025 challenge with a robust and modular registration pipeline. Our method begins with multi-way registration using cubic feet for feature extraction and quadro for global matching, and followed by a change-aware refinement step. To deal with the lack of edge information, we adopted a multi-way strategy that builds the registration graph from scratch. We also handled up to 10% outlier scans by filtering based on overlap ratio. This end-to-end pipeline allows us to register large-scale scans accurately and robustly, even in dynamic and uncertain environments. Thank you for your attention. Once again, we thank the organizers of NSS Challenge for making this competition possible. It was an honor to participate, and we truly look forward to next year's challenge with even more exciting problems. Thank you for listening.